So far, we've applied integration to a variety of settings, including finding the volume of familiar shapes, finding volumes of unfamiliar shapes in the case of volumes of revolution, and also finding arc lengths. Today, we take a look at another application of integration. These are problems that involve density, more specifically, a varying density. The basic method for problems with varying density will be the same as the method for solving our previous kinds of problems. We start by splitting the problem into pieces we know that are going to approximate the situation. We'll figure out the contribution of each of the pieces. If we then add up all of the contributions of each piece, we get an approximate solution to the entire problem. And then finally, we would get an exact solution if we took a limit as the number of pieces goes to infinity. Once we've done that, we recognize the solution as an integral. And once we've recognized that we have an integral, we have a variety of different ways we can complete the problem. We can use the fundamental theorem of calculus and one of our methods like integration by parts or partial fractions. Or if the integral is sufficiently complicated, we could turn to something like Wolfram Alpha or perhaps a handheld calculator. There are lots of different kinds of density. We're going to start with problems that involve what we call a mass density. So that would be something like kilograms per cubic meter. Now, if we're dealing with a mass density, we could figure out the total mass of a figure by taking the mass density and multiplying it by volume. That's assuming that the density is constant throughout the figure. One particular mass density that we'll use a lot in our problems is the mass density of air in the Earth's atmosphere. So this mass density is well modeled by the function given here. If we know the height above sea level, h, in meters, then the mass density of air, h meters above sea level, is given by this exponential function, 1.28, times e to the negative 0.000124h. And the units, because it's a mass density, are kilograms per cubic meter. So in particular, if we plug in h equals 0, we'll get the mass density of air at sea level. That'll be 1.28 kilograms per cubic meter. And then roughly a mile above sea level, if we plug in 1,600 meters, we would get F of 1,600 is equal to about 1.05 kilograms per cubic meter. And that is about 20% less than the density of air at sea level. Now, what about finding total mass when we have a varying density? So we might have a really tall figure, for example, that starts at sea level but ends, say, 100 meters above sea level, in which case the mass density of air at the bottom of the figure would be higher than the mass density of air at the top of the figure. So the total mass would no longer be just mass density times the volume because the density is going to change. That means we have to first split the problem into pieces that we know that have roughly constant density. We'll figure out the total mass of each of the pieces. That we can do with our simple formula, density times volume, because we are splitting the figure into pieces where the density is about constant. We'll approximate the total mass by adding up the contributions of each piece. We'll get an exact total mass by taking a limit as the number of pieces goes to infinity. We'll recognize that what we have done is in fact set up an integral, and then we'll evaluate it using the fundamental theorem of calculus or computer. For our examples today, I think we'll have one where we do Wolfram Alpha and one where we use the fundamental theorem. To find the total mass of air contained in the cone shown below, we have to slice the figure into pieces that have roughly constant height above sea level, because then we know that the mass density of air will be roughly constant on those pieces, and we can use that to figure out the total mass of air in each piece. The total height of the cone is 50 meters, the radius is 20 meters, and we'll call the height above the base up to a slice h sub I, and the radius of the cone, the radius of the slice r sub I, and the thickness will be delta h or delta hi. So we need to figure out the mass of one of our slices. Since each slice is a disk, we'll know how to find the volume of a slice, and because the disks all sit at roughly constant height above sea level, they have constant density. So the mass of a slice will be the volume of each slice times the mass density of air for that slice. The volume of a slice is something we've done many times with disks. This is going to be pi times the radius squared times delta h. But we don't want to have more than one variable, so we're going to get r sub I in terms of h sub I. We'll do so using similar triangles. So the inside triangle has a small side of r sub I. The outside triangle has small side equal to 20. The total height of the triangle is 50. And this one's we have a little bit of extra work to do because the height of the smaller triangle inside is not h sub I, because that's the distance from the base up to a slice. Instead, it's 50 minus h sub I. So the ratios of the sides, r sub I to 20, is the same as 50 minus h sub I to 50. I can solve for r sub I by multiplying through by 20. 20 over the 50 would give me 2/5. If I multiply that through, I'll be able to simplify a little bit, so that in the end I get r sub I is equal to 20 minus 2/5 times h sub I. So that's how the radius of our disk or slice changes as we move up and down in the cone. We go back to our equation for the mass of air in a slice. Remember, that's volume times density, and now the volume is pi times the radius squared, which is now pi times 20 minus 2/5 h squared, all times delta h. And now we multiply by the roughly constant mass density of air on this slice. For that, we use the model we have, 1.28 times the exponential evaluated at minus 0.000124 times the height. Once we have the mass of a slice, we can approximate the total mass of air in the figure by adding up what we would get by adding up the mass of all of the slices. So we would have the sum from 1 to n, and now we would just repeat what the mass of an individual slice is. Once we have an approximation to the total mass found by adding up the contributions of each slice, we can pass to an exact value for total mass by taking the limit as the number of our slices goes to infinity. So they get thinner and thinner and because of that, they do a better and better job of approximating the figure. And rather than write it all out again, I'll just indicate that we would write the same thing again, except with the limit sign in front. Next, we recognize that what we have done is in fact write down a Riemann integral. So inside the summation is where we find the function we're integrating. That's 20 minus 2/5 h. Quantity squared, and then the mass density function. The delta hi becomes dh. And we have to think about the limits. The lowest a slice can be in the cone is at a height of 0 above the base. And since the cone has height 50, the biggest h can be is 50. So our limits go from 0 to 50. Now that's an integral that we could actually do with integration by parts twice. We have a lot of messy constants though. So here I think we'll just go ahead and use Wolfram alpha to calculate the numerical value for that integral. There are a variety of ways that we could type in the function. Wolfram alpha is pretty good at understanding what we mean. The syntax isn't too fussy. So here's one way to do it. We just go ahead and click on the equal sign, and we'll get both a numerical approximation to the integral, about 26,767, and also a picture for it. To finish up our problem, we just note the numerical value. We want to pay attention to our units. What we were doing is finding the total mass of air. So those units are kilograms of air. Contained in the cone, and that completes our problem. In this example, we're taking a look at a population density problem, where the density of a population for a town decreases the further out we get from the town. Our job is to figure out the total population within 12 miles of the town center if the density is given by delta of r equals 10,000 over 1 plus r squared. The units are in people per square mile, and this is the r represents density in miles from the center. Now we need to slice into figures that are a roughly constant distance away from the center of town, so that the population density is roughly constant on that figure. In this case, thin rings will do the trick. You can think of this as concentric circles, because on a thin ring the population won't change much from the inside radius to the outside radius. And if the population density is roughly constant, we can figure out the population in a slice by multiplying the area of the slice by the population density. So in other words, if we know the area in square miles and multiply by density in people per square mile, we get total people. To find the area of a slice, we use some geometry where we envision cutting the ring and then kind of rolling it out or stretching it out. If we do that, we get something that's roughly a rectangle, and its length will be the circumference of the ring. That's about 2 pi times the radius, so 2 pi r sub I. And the width of the rectangle would be the thickness of the ring, or delta Ri. That makes the area of a ring roughly 2 pi Ri times delta Ri. That gives me the area of one of my slices of constant density, and it allows me to find the population contained in one of the slices. It'll be 2 pi Ri times delta Ri, all multiplied by the density, and that again is given by 10,000 over 1 plus r sub I squared. We can combine our constants to end up with 20,000 pi, r sub I on top, the 1 plus r sub I squared on bottom, and then all multiplied by the delta, r sub I. So that's the population in one slice. We could approximate the population of the town by adding up all of the rings, adding up the population on all of the rings. So that would give us a sum of what we had just written down. We'll save some time in this one and not write down the expression again. We'll note that the exact total population we could find by taking a limit as the number of rings goes to infinity. That would make them thinner and thinner, and so better and better approximations to the figure itself. That would be the limit of the sum, and again we'll save some time and not write down the expression for the population on a ring again. The idea is that what we are doing is creating an integral that represents the exact total population within 12 miles of the town center. So that's going to be the integral. The smallest r can be is right at the town center of 0, and the largest it can be is that ri can extend all the way out to 12 miles. So our limits go from 0 to 12. The function is the population on one of our slices, and the delta r sub I becomes the dr to tell us what the variable of integration is. This will be a little bit easier to integrate if I pull 10,000 pi out in front, kind of looking ahead to using substitution. It's going to leave me with a 2r, which note is the derivative of 1 plus r squared, dr. And we could use a w substitution where w is 1 plus r squared. And if we do, we'll end up with an antiderivative of natural log 1 plus r squared evaluated between 0 and 12 so that'll give me 10,000 times natural log of 1 plus 12 squared is 144. Looks like I've left off the pi there accidentally. But the final result will be about 49,767. Remembering our units, the units are total people, or the population of the town, and that completes the problem. That concludes our presentation on solving problems with varying density. Next time we'll take a look at solving problems that involve work, where the distance traveled will be the varying quantity instead of density. So that'll be next time.